OCF. Is that an obtuse crypto fish? The Organic Chemotaxonomist Federation? Obvious chafing factor? Our creatively functioning media industry is loaded with acronyms, and it is my hope that by the end of the next 20 minutes, you will understand this one: original camera files, or OCF. You'll learn what OCF are, why they are important to content creators, and the obstacles commonly found with managing them at scale. My name is Matthew Donato, and I've been on Netflix's video engineering team for over 5 years. OCF are important not just to filmmakers in general, but also to Netflix's globally distributed collaboration environment. These files, among other things, contain the data captured by a camera sensor. They represent the digital equivalent of a negative. Post-production processes, including editorial work and visual effects, cannot begin without them. There are some unique complexities to working with OCF that do not exist for typical Netflix YCBCR streams. A fundamental difference between them is that the data captured by professional production cameras generally contain raw, unprocessed sensor data that must be color managed before it can be viewed on standard computer monitors. Productions generate not only a lot of data, but also a lot of non-muxed audio that may be out of sync, along with proprietary metadata. All of this needs to be stored and organized. And this OCF data only constitute fractions of the final cut. This allows us to be choosy about what types of OCF data get sent over a network. By addressing these challenges, we can remove the technical burden that is sometimes placed on our artists and creators, which in turn can bring them joy while developing original, creative footage. Digital studio workflows. Digital studio cameras are manufactured by companies like ARRI, Blackmagic Design, Canon, Panasonic, Panavision, Red, Sony, and more. These high-end camera systems are uniquely designed with individualized features like prime lenses, high bit-depth sensors, and efficient compression algorithms. Because of this, camera systems often use custom and proprietary data formats which best exploit the camera's hardware and software. And film studios choose specific camera systems because of these unique attributes, or secret sauce, which make them more desirable or even appropriate for use on different film sets. Nonetheless, OCF video data is complex. Proprietary software tools are then often required to read, decode, and otherwise render the mosaic sensor data in a way that accurately reproduces the scenes as they were recorded. These processes are often compute-intensive, and while GPU and CPU solutions exist, they do not always guarantee real-time playback of full-resolution mosaic video. In the post-production world, these proprietary camera systems lead to bespoke workflows. Depending on the camera systems used, each post-production workflow is as unique as a snowflake, which makes OCF processing that much more challenging to scale. Our goal is to utilize the cloud computing and storage resources that we have solidified for the Netflix streaming platform to offer comparable features and scale to post-production processes of our original content. Although technical specifications of the capture formats are more varied, they do share some similarities. And there are a number of open standards that we can utilize to process and organize camera footage efficiently. For that, we'll move on to some acronyms that aren't OCF. Welcome to the industry-wide acronym jungle. If you stick with me, I'll point out 6 acronyms that will help you understand the tooling we rely on to bring joy to our creators. They are ASC-CDL, LUT, ACES, AMF, EDL, and OTIO. A CDL is a color decision list. It's used to communicate point operations on RGB images, both on-set and in post-production. It was developed by the American Society of Cinematographers, or ASC, and contains 10 decimal numbers that serve as variables to point operators on RGB color values. The first 9 numbers are triplets of slope, offset, and power, commonly written as SOP, and impact an image's black level, white level, contrast, and gamma. The 10th number, saturation, or SAT, is self-explanatory. Don't let these measly 10 numbers fool you. CDLs allow for drastic color manipulations, but with great power comes great responsibility. The ASC CDL standard does not contain metadata to describe what color space it should be applied in. In other words, using a CDL developed for a Rec. 709 image on a Rec. 2020 image is an obvious colorimetric fallacy. You might have already heard of lookup tables, or LUTs. Like CDLs, LUTs are applied as point operations to modify RGB image values. They are often used when the mathematical operations necessary to perform a color transform is more complicated than what can be described by a simple power function or a CDL. There are several syntactical standards for LUTs, say that 5 times fast, and the example shown here would have a .cube extension. Having a comment line to describe the LUT's input and output color spaces is helpful, but if this comment is missing from the header, it's practically impossible to use. Lastly, applying LUTs to RGB images, particularly LUTs with high precision, can be a compute-intensive task, just like demosaicing. So we've just described ways to modify image values, but have not yet talked about the color spaces in which those operations can be applied. The Academy Color Encoding System, or ACES, was developed by the Academy of Motion Picture Arts and Sciences and is documented in SMPTE-ST 2065-1. Its initial release was in 2014, it is actively maintained, and has been used on hundreds of movies to date. Its images are contained in 16-bit floating-point EXRs, which are precise enough such that vital color information is not lost or compressed. Its AP0 color space is wide enough to describe practically any color that can be perceived by the human visual system. It has a linear transfer function. The ACES standards are extensive enough to be used in a variety of post-production applications. Because of these specs, ACES images don't look right when they're just open for preview. The AP0 color space is wider than the sRGB color space found on most monitors, which makes ACES images appear desaturated. The linear transfer function makes their contrast appear reduced, and that's really because ACES linear AP0 images are designed for encoding, not viewing in that form. The colorimetric transforms that ACES describes enable conversions for proper viewing. There are several transforms included in ACES, starting with the conversion of typical camera or encoding color spaces into ACES, a conversion from the scene-referred ACES values to idealized output-referred display values, and finally, a conversion that maps to the color reproduction characteristics of typical displays. This last step is what makes the images look correct. If that felt like drinking from a fire hose, just remember this obvious, concise phrasing. ACES tooling effectively replaces assumptions about colorimetry with explicit declarations. In our world, AMF doesn't describe a bowling alley chain, but rather an ACES metadata file. An AMF rides along with a video or image sequence in a sidecar XML file that carries instructions to properly recreate the ACES color pipeline that was used to generate the image. It is not limited in scope to ACES-defined color transforms. For example, its schema contains elements for other color transforms that are CDL or LUT-based. And it enables this by defining input and output color pipelines so that CDL, LUT, or other operations can be performed in the context of the ACES spec. We're doing great. Just 2 more to go. We're shifting now from color-based acronyms to time-based acronyms. Just as there are an abundance of color transformation specs, there's also an abundance of timeline specs. An EDL, or Edit Decision List, is an ordered list of events that conform captured clips to a temporal position on a movie's timeline. One straightforward EDL implementation is shown here. In this sample, the EDL events are shown in white and contain, from left to right, an event number, a source tape name, a source type, V for video, a transition type, C for cut, and 4 timecode values. The first 2 refer to the timecodes in the source media from which to cut. The second 2 refer to the timecodes in the resulting timeline to which the source material should be temporally mapped. If that's a bit tricky to visualize, let's turn to our final acronym of the day, OTIO. OpenTimelineIO is an interchange format for timeline information, as well as an API for manipulating timeline data. Shown here is the OTIO View UI, which can import a variety of timeline formats. I've imported the 2 events from the previous slide. There's only 1 video track and the 2 timeline events, which are showed on the single timeline side by side. Stepping backwards, you might have noticed that each of the two events had ASC CDL values in blue. They're technically comments, but they serve an important utility. For some formats, OpenTimelineIO can also read the comments from an EDL. This EDL's CDL values are nested under each event. If you're feeling experimental, check out OpenTimelineIO's latest release. It's in public beta. Pop quiz! It's time for some acronym math. Bet you didn't expect that. What could be built by leveraging both AMF and OTIO? It's not aimfoot, but combining these tools lets us open collaboration freely and effectively for editorial work. That way, this jungle of acronyms and technology does not burden our content creators. Powering media workflows. Let's get on set and shoot some footage. Actors are having their hair and makeup done, crews are setting up camera rigs, electricians are striking lights, directors are getting ready to call action. And there are hours, if not days, worth of footage to be generated. A typical studio production is incredibly data intensive. For example, on one of our unscripted reality shows, the filmmakers used 12 individual cameras, manufactured by 3 different companies, generated 8 terabytes of data on a single day, and shot for 8 days. The footage was shot on 3 different types of storage media or memory cards. In general, productions collect these massive quantities of data because they need ample coverage of a scene. This means directors shoot takes multiple times from multiple angles, giving editors the flexibility to construct a seamless final cut. And it's common for a final movie to only consist of about 5 to 10% of the original media captured. When a shoot is finished, data wranglers ensure that every bit of camera data is backed up in triplicate because it was so expensive to generate. We use a 3-2-1 model. 3 copies of the content on at least 2 different storage media where there is at least 1 copy far away in a different physical location. Nowadays, much of movie and television production is globally distributed. Movie sets are in many major cities, while visual effects and editorial work take place wherever an artist is sitting, and that's usually somewhere with a decent internet connection. At Netflix, we're focused on centralizing and organizing camera media in a couple of ways. The primary focus is on our content creation ecosystem called Content Hub, which enables production teams to import, inspect, and validate OCF. The metadata we ingest enables us to organize the media into categories such as scene number, take number, or day of shooting. Furthermore, requests to demosaic raw video, trim it to fit a timeline, or convert it to a viewable format can be accessed from the same interface. Additionally, we provide external APIs for our creative partners to exchange files and metadata in the cloud. These integrations utilize third-party tools that post-production partners are already familiar with. On the Netflix streaming side of things, we already leverage media inspections, which are important to all of our encoding workflows. Inspection algorithms generate all of the technical metadata about the assets in our system, such as Netflix originals, licensed content, marketing materials, and more. In the case of OCF inspections, data arrive on Content Hub as either a camera roll or a sound roll. These are terms that describe the incoming OCF from a single memory card or camera hard drive. This can be thought of as the digital version of a film magazine. Our inspection algorithms then determine which contents describe a single clip. A clip refers to the recorded range of information bounded by the time between when a take started rolling and when it stopped rolling. Inspections also look for proxy media, which are demosaiced and usually compressed frame-accurate copies of the mosaic raw video. These proxy media are used for editorial work because they can be decoded more easily in editing software. To tie it all together, inspections are guided by OCF metadata, which can be embedded in the raw video or delivered separately as text-based sidecar files. Some ordinary common fields of the metadata collected and produced by inspections are shown here. They encompass information about the camera, image, timecode, or frame number, recording and playback rate, scene and take, sensor gain factors, color temperature, sensitivity, etc. Beyond just those technical details, we can also utilize inspections to identify qualitative issues in the content itself, like detecting dead or stuck pixels, or maybe non-continuous timecode. These data are deposited into our asset management platform and operated upon based on business logic within the parent media workflows. Okay, it's time for a demo. We've used OCF inspections along with other workflow tools on several of our original productions, including La Casa de Papel Part 5. Let's take a look at the Assets page on Content Hub. This is where a content creator would go and review all of the media after it has been ingested and inspected. The UI shows still frame previews of the media, and on this UI, we can also see some of the inspection metadata. So we've already seen how much data and processing power is needed to decode and organize OCF. But for actually cutting or editing a movie, these behind-the-scene processes are secondary. Editors cut film using intermediate or proxy files, which are significantly lighter in the file size and have been transformed to a display's color space. But when it comes time for final color grading and visual effects work, creators must refer back to the OCF to ensure they are working with the images at their highest quality. Content creators need to retrieve the OCF materials from Content Hub, but they don't need every single frame or audio sample from the camera or sound roll. They only need those that made it into the final cut, plus a few frames or samples buffered at the head and tail of each edit, and these are known as handles. On the technical side, downloading tons of OCF is neither network nor storage friendly either. So to obtain only the OCF needed, creators will export their editorial decisions as an EDL file. This EDL can be very simple or complex, containing up to hundreds of events or more. And earlier I mentioned that raw video data are often proprietary, so we can't just, trim them at iframes because their compression schemes might not even have detectable iframes. So how do we isolate the specific data needed in conforming the editorial timeline with the OCF? We submit a conform pull request in Content Hub. All right, here's another demo. So we're back in the Content Hub UI on the Mailbox tab. This is where we can create a new submission, which is a way of requesting some sort of OCF processing. There is a growing list of processes we support, but for this timeline, we're submitting a conform pull request. The vendor field tells us to whom the conform pull should be delivered, and the submission name is a custom string for our own reference. Now, we need to tell Content Hub which frames to pull. To do this, we'll import an asset list, which points to an EDL file. We'll tell Content Hub to match clips based on their real name, select the EDL's frame rate, and specify the number of frames to use for handles. After import, Content Hub identifies all of the events from our EDL. Under the hood, Content Hub is searching that footage workspace from before for clips with matching real names. Once it finds them, it submits requests to our media processing system to spin up instances that run the conform pull trims. After it's complete, Content Hub populates some additional information about the output media verification, such as its format, the number of files in the conform pull, and the final size of the media. Finally, we can tab back over to the project's workspace to see the output of the submission, along with the EDL that we ingested. And that's it. These assets are ready to be downloaded and relinked for color grading and visual effects. Several internal tools were developed to support these efforts. We've already touched on inspections, which occur during ingest. There's EditDroid, built on OpenTimelineIO, which enables querying information from matching EDLs to the large libraries of media. There's also Sagan, which is the name of our media processing system. It handles not only OCF processing operations like conform pulls and VFX plate generation, which wouldn't be possible without ACES, but it is also capable of kicking off the media inspections and non-OCF media across Netflix. And Sagan is built on Cosmos, which is the name for our microservice-based application that enables high-throughput, asynchronous media workflows. The number of use cases for OCF processing continue to grow, and we are actively exploring them to bring joy to our artists and creators. It is our hope that the joy we bring to them is extended for our community folks. I mean members. I would not be presenting today without the contributions from my teammates, and would like to thank all of those who helped me develop this presentation and those who worked tirelessly to bring to fruition the tools and all the features that I've shared and demoed with you today. Thank you to the Demuxed team and their sponsors. And thank you for joining me. If you're interested in bringing joy to our content creators and members, we're hiring, so be sure to check out some of the open, challenging functions across Netflix by visiting jobs.netflix.com.